Bentornati, prendiamo posto.
Welcome back. Please be so kind as to take your seats so that we can start the afternoon session of the 19th edition of JTF. Thank you very much for being with us. And now I'd like to introduce the first speaker for this afternoon session, Susanna Testa, researcher, professor at the design faculty at Politecnico. She's devoted to technological innovation in the fashion industry. She's a professor. She holds classes at the design faculty of the Politecnico di Milano. And she works with manufacturing technology and fashion drawing, portfolio and digital branding. She's active as an illustrator, a designer of fashion items, and she's also the founder of Panello. She's now going to present us the design of the future jewelry in the digital era. She's going to present us with the digital future of jewelry. She's going to explore innovation in this industry by means of digital processing, with the impact on creativity, the choice of material. The case studies will pinpoint to new opportunity for creativity through digital technology to try and be creative and competitive. I see that she's already online, so I'd like to welcome her. Good afternoon. I hope that you can hear me very well then. So again, good afternoon. Thank you very much for having me. Thank you for your kind introduction. I'd like to thank Lego. I'd like to thank Vicenza Ora, Italian Exhibition Group, and the whole organization for this wonderful opportunity to share knowledge. I'm very sorry I couldn't be with you in person. My name is Susanna Testa. I am a researcher and professor at the design faculty at the Politecnico di Milano. I deal with design and innovation process in the jewelry industry and accessory industry. I'd like to share my desktop with you. I hope you can see it. Could you please confirm? Can you see the presentation all right? Very well. Thank you. So, as was said, I'm going to talk about the new scenario for jewelry as introduced by digital technology in the value chain, and I'm going to share with you a number of case studies to that purpose. Now, before I start about the future scenario for the industry, I'd like to make one step backward and invite you to think about what is jewelry for you. Each of you should try and come up with a definition and perhaps also associate an image with what is jewelry to you. So my question is this a jewel? And I believe that you'll all agree on that. This is a pearl and diamond pendant that was owned by Marie Antoinette, the last queen of France. She was well known for her lifestyle, and before being made praise, she had collected all her jewels to be sent to Vienna. And this piece of jewelry has been sold by Sotheby for over 36 million in an auction by Sotheby. Now, I'll move on to another example, my second example. I'm going to comment on this video, asking you whether you believe that this is a jewel. I'm going to talk about this startup company, Pan Generator, creating jewels with light. This is a necklace that is made up of light, which is projected over the body of the model, of the person wearing it, through the smartphone. This is an app, dedicated app generating this necklace, McClooney, an ornament which is just made up of light beams. So this is a comparison between two very different types of jewelry. On the left-hand side, you have an historical object with precious materials. On the right-hand side, you have an interactive jewels that has lost all its physical aspect, and it is indeed only the projection of light over the body of the wearer, becoming just again this lit-up surface with a constantly changing shape. And this obviously is quite different from the first item I showed you. And we may say that for jewelry to be considered as such, obviously it has to be made up of something precious. Over the past 2 centuries, the concept of craftsmanship, of man-made, handmade, has taken up an important role in attaching value to a piece of jewelry. In the past, and I'm being oversimplistic now in telling you that, well, the past can be presented as a straight line where value is associated directly to the craftsmanship, to the use of precious metals and materials. With the Industrial Revolution, we shifted from a system that was based on craftsmanship onto new industrial manufacturing models. Craftsmanship has been sided up, flanked by the use of equipment with an advantage in terms of time for development of these jewels and for the number of jewels being manufactured. It is during the Industrial Revolution that we show the shift from jewel made through craftsmanship to the jewels made at industrial level. So basically we shift from handmade jewel to the machine-made jewel. This is a kind of opposition between these two approaches that have marked all different industries and all different type of art objects as well. Jewelry has been involved also and touched by this basically opposition between being handmade and being machine-made, something that has been brought about through the Industrial Revolution. So two completely and opposed different processes have then been developed. So we have, on the one hand side, handmade jewels that are handmade, that are unique, made to measure, whereas on the other side we have industrial jewels that are standardized, that are accessible and democratic, and that are sold on the mass market. Here you see that increasing the value of the material, increasing the craftsmanship, you have a parallel increase of the value of the final object. After the development of the 20th century, we've have a disruptive effect on that linearity. In the 20th century, basically, not always is the value associated with the time used to make a certain jewel, with the price of the materials being used. Indeed, the price can also be the result in terms of intangible qualities. Defining today what a jewel is quite difficult, because in the jewelry industry we have a lot of fragmentation, a lot of different and diverse labels and keywords. So much so that at times we might find also things that are in contradiction one with the other, labels that are in contradictions. So I think that in order to try and create some order, we should come up with perhaps a different vision. These words have come up after the changes that have been recorded in the industry as detected by project research that was carried out at the Politecnico di Milano. These keywords refer to the meanings that a piece of jewelry can take up. So a jewel can be functional, it could be used, for example, as an object of beauty and be just an ornament or act as a function, or it could be a magic or symbolic object. If we try and look at different words and group them together, for example, research, handmade, or mass production, digital manufacturing, or communication, well, this has to do with the complexity of the project, which requires a supply chain that is often diverse and non-standardized. Indeed, it changes based on the different requirements. Another theme cluster looks at the different disciplines that may be required, as, for example, engineering, art, or perhaps anthropology and chemistry, or archaeology and material sciences, different disciplines that contribute to the making of a jewel. The actors, the players, also play an important role in that. Basically, a piece of jewelry is the result of the work of different companies, manufacturing companies, the designers, and those who choose it and sell it through the retailers. Looking at values, values are intangible, but it is indeed what guided the orientation of the brands in the world of jewelry, even more so than the uniqueness and preciousness of the material. These values are connected to the main features of our company manufacturing jewels. So there's no one single definition of a jewel. There are indeed different interpretations based on the processes leading to the object or to the wearer ideas. So basically, it is extremely fragmented. How about the future? Well, in the future, we can only think about possibilities, looking at what the present trends point out to. So we can look at trends at the state-of-the-art, at the avant-garde movements that may lead to potential future developments. Identifying something that may be in contrast with the present situation. Analyzing the macro trends that can be detected worldwide, the industry, and that bear on the different habits, on the aesthetics, on the wearer, we see that digital technologies is playing an ever greater role in the different sectors of human activities. We know, for example, that in the digital zines, we know that these are very important players as they influence, importantly, purchasing decisions. Oftentimes, consumers, even when they buy offline, they are greatly influenced by what happens online, i.e. information, advice got, again, online. Corona basically further promoted this digitalization process that was already underway before the corona breakout. As for jewels, digital technologies certainly are closely related to the chain value. It affects the characteristics of the process, of the products, and of the services connected to jewels. When we talk about processes, well, processes are those shifts that make sure that an idea is translated into a product, i.e. the concept of production, marketing, distribution, sale, customer care, use, disposal, and second life, the repurposing of the jewel. The product is the object which is manufactured or handmade to meet the requirement, the desire of consumer. And then there are services. Services that are the intangible activities that are carried out to meet the needs of a specific target. And then experiences, that is, that set of interactions that involve perception, mutual perception, as well as emotional aspects between users, products, brands, and services. The digital revolution has brought about a lot of fluidity among the above, so much so that there is no isolation between the different items, and indeed there is a much closer cooperation and blending of these categories, so that the distance is reduced between what is handmade and what is machine-made, with the opposition being done away with, because now basically everything is much more blurred. So exclusivity and inclusivity are not are opposites again, as is customization and bespoke, as man-made and mass-produced, artificial and pure raw materials. The inert raw material and the dynamism of the animation. We have basically all the different categories joining together, being much more blurred, with no such clear-cut distinction as was the case in the past. So we have, for example, artificial intelligence contributing to normal efficiency, normal intelligence. So the main difference between man-made and machine-made is still present also when it comes to jewels, but through digital revolution, there's much more, again, flexibility, blurring between the two. All the dichotomies have become ranges, seamless ranges of different options. Through digital revolution, all the actors along the pipeline are mixed up together. And this pervasive integration of digital technology has influenced the value chain from design to distribution and consumption. This research project is the result of the analysis of the market trend as detected by different case studies, and it is also the result of experiences of a project that we have developed at the Politecnico di Milano. I'm now going to show you examples of this fluidity, of this seamlessly. And I'm going to start from the concept through the production to the interaction with the product, the use of that, down to retail and communication. At the concept level, digital technology and artificial intelligence, together with design, are enabling a much faster development of a design. Artificial intelligence may be used also to generate models. So the designer basically is using digital technology, as for example 3D printing, additive printing, to transfer the design into an object. You can have, for example, a resin-made 3D model for your jewel to make it finally become a traditional jewel. This brooch, Enchantress brooch from Folund, has been developed through algorithmic design and AI. This has been printed with a 3D printing machine, and then has been further developed and finished with a handmade approach. So basically, by means of AI, we could create a whole variation of different shapes, not just design that is, but all the human actions can lead to different results. In this case, the process and the product are closely interrelated. The craftsmanship, human creativity, and AI and algorithms are all blended together and interrelated. Digital co-creation platform open up a new area for cooperation. Designers may design processes rather than design the final object. Design, therefore, is obtained through paradigm generating endless variations with a structural consistency. One example is a generative study that combines technology, art, using 3D printers and digital platform to create customized products. Users may interact with the graphic interchange, developing variations that are inspired by nature or by fractals mathematics to come up with custom design single pieces. Here we see a blurring between customization and standardization, between physical and virtual, between creativity and AI. Latest technologies may enable designers to involve consumers and users right from the early stages of creativity, coming up with a product that meet their requirements and generating emotional experiences. An example and case is this 3D orchid by Minale Meda that can be attached to suits. The shape of the flower is generated based on the season, the location where the user is based. In case the user is unhappy with the result, a new creation can be developed based on new features. This basically stresses how important the local dimension is, with the possibility to have a 3D printed model locally based on the local characteristics in terms of the soil conditions, the weather conditions, and so on and so forth. Here, this is Nuange and Apesanteur by Boucheron. It is a necklace that basically refers to necklaces obtained through logarithms with over 4,000 white stones and drops of glass on titanium wires that are as thin as human hair. So you see that virtual models together with the engineering can be mixed up with the craftsmanship, the different matters, and human creativity. Digital technologies have permeated the products to make them able to record data, store data, and making them liable to different behaviors and to change based on the conditions of the wearer. This is the case for of certain wearables, Aura being one of them, where you can measure the health, the amount of sleep of the wearer, sharing such data with a smartphone. These are made-to-measure software items, basically. They detect the different features of the wearers, and the frame is mass-produced. These are tangible objects that are dynamic at the same time because they can record and send information on an ongoing basis. They enable different users to exchange data and establish digital conversations. There are other projects with integrated technology that are extremely dynamic, even from the physical point of view. Over time, for example, changing the input, either willful inputs or non-willful inputs, change color. Oyster is a project launched by the Politecnico di Milano. It includes a number of sensors, so much so that the shape is changed based on the emotional condition of the wearer. Retail and communication have been permeated by the change that were implemented by digital revolution. For example, augmented reality, mixed reality, the metaverse have been disruptive vis-a-vis the way we interact with the products and convey information. Virtual reality enables clients to try on products in a digital environment. The augmented reality introduces digital element in the real world. This is useful in the world of retail to visualize products or specific physical spaces to enrich education, to enrich also advertising. Mixed reality combines augmented reality and the real reality. And the metaverse is a further development of such technologies, thus creating a digital shared environment where users may interact as avatars. And this adds to the possibilities that retailers may use, as the case for exploring virtual shops and stores, for example, or attending meetings. Well, these technologies are, in a way, changing dramatically the way we make our purchases, and they are also changing the borders or the boundaries between the digital world and the real world. I'd like to quote this example by Maria Tash, which is a try-on digital tool. In this case, the software of virtual try-on enables users to visualize piercing different earrings and try them on, basically, on their body. Here we break away with the borders between physical and virtual. In this platform, you can try on virtual jewels that may be worn by means of augmented reality, virtual space, and mixed reality. The jewels are physically developed in limited editions, and when bought, the purchaser is given the digital format with a link to a filter enabling them to wear such accessories as bought through the platform. Using Google Meet, Snapchat, or other virtual platform for a conference call. So you see that the object is moving. And when it comes to top-of-the-range jewelry, this opens up again to virtual products. This is the Genesi collection by Dolce & Gabbana. That is in a way somewhat in between the two worlds, with virtual NFT as an impossible tiara that you see here, which is actually made with imaginary stones that have no connection with anything physical. And then there are other physical objects that are included that may be bought individually. So the collection basically is a totally virtual collection that was sold at an auction for $6 million. Here we have a top-of-the-range collection, including NFT, through a technology event which is called Vivatech, held in Paris, which is the most important technology event in terms of startup in Europe. And this collection Bien Wonders is the combination of traditional craftsmanship and digital solutions. And the objects could not be physically be obtained in the real world. At the Politecnico di Milano, we are experimenting the possibilities that are made possible through the new technologies. This is the project devoted to jewels. Utopia is the title of the project. The main objective was to explore the designing project of a collection of virtual jewels that was conceived to be worn in the digital world. The concept of the jewels have been developed with the use of artificial intelligence. And the objects have been exhibited in an ad hoc show, virtual show. Artificial intelligence and digital technology may be used also for communication purposes. Through AI, a campaign has been put together, and the images that you see are the result of prompts, of inputs that and of the iterative dialogue with the artificial intelligence. So the faces that you see here depicted are not real, but are only similar to what is possible faces. So you see that in the system of jewelry, we have much more blurred boundaries. And you see that these new models of jewelry tell us about contamination, exchange of knowledge, an exchange of different disciplines, even far away from the world of jewel, as is the case for gaming, to create immersive reality. Cartier in 2021 has entered a partnership with Fashion Gaming to promote their collection, Clash Unlimited, through Dress. The Dress is a platform that enables users to create and customize apparel, jewels, and to see them as worn by avatars. Another more recent example of a combination between the fashion industry and jewel is this cooperation with Bulgari to develop an online collection. 1 million hits have characterized this object. So what about the future? What do we expect for the future? I have shown you state-of-the-art, very modern examples, but these examples can identify some trends that are not pointing to the replacement of productive models or the doing away of certain professions, but rather they point the way to a coexistence and the blurring between the real reality and virtual reality, craftsmanship and engineering, what is real and what is not real, human creativity and artificial intelligence. So the future is not going to see a replacement, but is going to be an opening up of new horizons with the new connections ensuing. Thank you very much for your kind attention. I'm sorry I won't be attending the Q&A session, but I'm going to leave you my mail. So should you have any questions or doubts, please feel free to write to me directly. Thank you very much. So this is all on my side. So maybe we can take questions immediately if there are urgent questions from the audience. I don't see anybody asking for the floor, so I'd like to thank Professor Testa for her presentation. Thank you.
L'attore, in questo caso,
So now the second speaker who is here with us, Stuart Grice, who has more than 30 years of experience in the world of jewelry, in particular in the production of alloys, implementation of processes, technical assistance, and production control. He's a vice president of Hoover & Strong, Richmond, Virginia, a member of the Institute of Materials, Minerals and Mining, and engineer of the Engineering Council of Great Britain and Northern Ireland. And he will tell about solders, and we have a presentation which will explore the criteria in order to evaluate the good application of solders and determine whether it is possible to identify guidelines to see what solders will work better in specific situations.
Absolutely no idea what you just said. Thank you. Okay, so I'm going to talk about solders today, and this isn't a heavy technical presentation. It's more of a hands-on sort of investigate it in the factory type of presentation. So what makes a good solder? Can you all hear that okay? Am I good? Yep. What makes a good solder? Is it how it flows, or is it how it wets? Is it its strength, or its melt gap, its hardness, its ductility, or is it a combination of all these properties? After many years of working in technical support within the jewellery industry, I've experienced many examples of one jeweller saying a certain solder is the best solder they've ever used, it's brilliant, it's great, and another jeweller saying the exact same solder is complete rubbish and it's no good, they can't use it. So why is that? So what we want to try and do is to quantify in simple terms some physical and mechanical properties for solders and joining, so we can predict how the joining process is going to perform. And are some solders better suited for joining applications than others? So see if I can get this right. Yes, there we go. So it's the most common form of joining in our industry. Any bench jeweller, any volume manufacturer has to manufacture the soldering process to make their product. Companies that supply solders, they supply them in various forms, and they all have their own unique formulas, usually to suit, colour match their own mill products, sheet wire, etc., castings. And their aim is to give you, the jeweller, problem-free joining without damaging the parent metal or any previous soldered joints. So this study started when a problem occurred that wasn't there before at the company I worked for in Richmond, Virginia, USA, Hoover & Strong. And it was during solitaire manufacturing. And initially, defects were noticed when we soldered 14-karat white heads to 14-karat white shanks and 14-karat yellow shanks, and they both used the same solder for the assembly. So if anyone is unfamiliar, I'll quickly go through the manufacturing process for a solitaire. So the head components are stamped from sheet, they're assembled together, and then they're soldered. And then the shank is made, usually from wire, and it's die struck, and then this is soldered to the head. And then the inside of the solitaire is sanded to get ready for final finishing. And after inside sanding, our finishing department, they noticed that there was an increase in the incidence of porosity in the soldered area, and this was getting worse and worse. And it meant that more repairs were needed to make acceptable product, and therefore it was more cost and more time. Scrap rates eventually became unacceptable, so some investigation was needed. Here we have a few examples of rubbish heads. So when we examined the process, it wasn't only the joining of the head to the shank that resulted in porosity, it was also when we made the heads themselves. We had porosity, we had voids, as we can see here in these couple of examples. Initially, the solder was blamed, and the investigations all focused into the area of the solder to try and identify this problem and then to try and eliminate it. And after starting this study, the type of defect started to occur in several other head-shank combinations using different solders. So it became obvious this investigation needed to go deeper. It also became apparent very quickly that the scope of the investigation was going to be huge. We stock 50, maybe 60 different types of solder, and so to examine and characterize all of our solders was going to be a very large task indeed, so we needed to focus a little bit more. So really, what this study about is, it's not a study on solder compositions. These are all very well documented. People that make solders know them. It's not a study on solder development and how to make the ultimate solder. It's a grassroots analysis on what does and does not work. So we decided to investigate several solders around a common carriage, but with different compositions, flow temperatures, and melting ranges. We'll document some simple experiments to investigate wetting, flow, joint geometry, and we hope to determine what variables have the greatest effect on a successful soldering operation. And hopefully from this we can form a guideline to look for what is apparent when selecting a solder and a process. And I'm going to skip that side. So there are several basic principles that apply in jewelry applications to achieve successful solder joints. And one of the most important aspects is joint preparation. All parts must be a tight fit at the interface. And there are many joint configurations to choose from. We have butt joints, lap joints, T-joints, strap joints, many different types. The choice is going to depend on what you're making and what makes it aesthetically pleasing. Joint faces always need to be clean for wetting to occur. So filing and sanding is recommended to clean away dirt and grease. And the surface roughness is also beneficial because it can help by reducing the contact angle of the liquid solder, so it enhances the capillary action. And there are several basic methods of soldering. So at the bottom, sort of base level, you can use a gas torch, which is what a bench jeweler will typically use. You can use an atmosphere-controlled batch furnace for batch production. You can use an atmosphere-controlled belt furnace for continuous volume production. And you can use induction heat sources. These are typically used in things like chain manufacturing or high-temperature solder applications. So when torch soldering the joint, the area must be heated and not the solder. Everybody knows this who's a jeweler, but it's worth reiterating. Solders always flow to the area of greatest heat and not away from it, so that's how you do it. Time at temperature should be kept to a minimum to prevent excess flow and excessive diffusion of any excessive diffusion into the parent metal or any volatilization of low melting point constituents from the solder, which can lead to porous joints. Both torch and furnace methods can use solder paste, but we're not going to go into these for this study. They're an entirely different study that could be looked at some point. So, the World Gold Council outlines the basic requirements for a solder alloy. So first of all, it's got to be of the correct carriage, or as we call plumb in the US. It's got to be a good color match to the parent metal. It's got to have suitable mechanical and physical properties, so strength, ductility, wear, tarnish resistance. It's got to have a liquidus lower than the solidus of the parent metal, or metals. It's got to have a suitable melt range or melt gap. But most importantly, it's got to be able to be primary manufactured into sheet or wire by a solder manufacturer. There should be no problems with melting or casting, rolling, or scrap recycling. A solder can be great for joining, but if a supplier can't make it into a saleable product, then it's not a good solder. Next slide. Here we go. So it's generally accepted that solders should have a sharp melt gap for the best results. For gold solders, this often means they are based around the eutectic valley in the gold-silver-copper system, and this not only keeps the melting temperature low, it also keeps the melt gap narrow. Some solders do have quite broad gaps, but this is usually a design around color considerations and where they sit in the soldering process. Color match can also be difficult the further away a solder is from the parent metal in melting range. As a general rule, easy and extra easy solders tend to be inferior to medium and hard solders as far as color match goes, particularly when you're talking about yellow gold solders. The elemental additions you have to put in there to depress the melting point, such as zinc or indium, tin, gallium, and in the US, cadmium. These are all commonly used. These tend to affect the color, particularly when you're looking at yellow solders, and they bleach them. And it's well documented. I know in Europe you typically don't use cadmium solders, but they do in the US still. And cadmium does improve flow and improve wetting, but it's very toxic. So I'm not going to go into that, but I'm sure everybody understands the dangers of cadmium, sorry. So to start the project, we did a survey of solders and their published temperature data from 3 solder suppliers, one of them being the company who I work for. And this is what we found. So none of this data that a jeweler or a manufacturer gets is composition-based. It's just published data on melt gap, melt range, and whether or not it contains cadmium. Regardless of what else there is in there, all but one example of the cadmium solders cadmium-free solders rather, has a narrower melt gap than the cadmium-containing solders, which should be very beneficial when used in action. So let's have a look at some of the experiments we looked at. So, as I said before, we wanted to look at the effect of solder composition on joining performance for all carats and colours, but this is way out of timescale, way out of budget. So we concentrated on 14-carat solders. The bulk of jewellery in the US, and indeed, I believe, in quite a lot of Europe as well, is made from 14-carat, so that's what we decided to look at. And jewellers don't know the composition, nor manufacturers if they don't make their own solders. They don't know the composition of the solder they buy, nor do they have access to that information. Manufacturers tend to guard their formulas, and they don't give this information away. They only give the information on whether cadmium is going to be in there or not. So with this in mind, we decided some simple tests to compare solders based on the information available to the jeweller. So the colour, the grade, what the melt temperature is, what the flow temperature is, and whether or not it contains cadmium. This is the only data that's typically available to the purchaser. So we chose a relatively simple study. So we did 2 14 yellow cadmium-containing solders, we did 2 14 yellow cadmium-free solders, and we did 2 white cadmium-free solders. And again, as you can see from these melt gaps, the cadmium-free versions do have narrower melting gaps than an equivalent cadmium-containing solders. So the type of test we're going to look at, we came up with. On the small scale, a bench jeweller usually works on individual items, one at a time, using a handheld torch, so an open flame, as the heat source. A volume manufacturer is going to assemble multiple items at the same time using jigs, usually in an atmosphere-controlled belt furnace. And you can see a little example of those on the picture there. So for this study, each test is going to be processed in these 2 ways. For torch soldering, boric acid was used as a flux to protect the workpiece, and in belt furnace, cracked ammonia was used as the protective atmosphere. And we hoped this approach would highlight any differences in solder performance between the 2 methods. So the first test we performed was a wetting test. So we took 6 pieces of each solder and we placed them simply onto a piece of carat gold sheet, and then they were melted using the 2 methods outlined above. This would give us an indication of how well the solders wet the parent metal under each condition. And as we can see from the results table, all there on the second top column entitled torch, the torch soldering tests all showed full liquation, the solders wetted okay, there was no balling, there was no evidence of residual solder left. There did not appear again to be any noticeable difference between cadmium and cadmium-free solders. Solder B in the furnace test was by far the worst result. and there seems to have been some liquation of the pieces, but no discernible solder flow and no wetting on the sheet. I think that pointer, this is what I'm talking about. It looks horrible. Solders ENF, that are the white gold solders, we showed signs of some wetting in the furnace tests, but again, we could see some of the residual solder pieces in there. So the furnace results may be exhibiting a phenomenon where diffusion of the lower melting point constituents in the parent metal raises the flow temperature of the solder remaining in the piece to a melt point above the temperature set furnace, the set temperature of the furnace. So the remaining solder doesn't melt. Also note that the worst result was solder B, and it came with the solder with the largest melt gap. So from these results, we can possibly say that the solder's chosen are more sensitive to furnace conditions than direct torch. So after that, we decided to do some tensile tests. Excuse me. So a quantitative measure of the strength of a solder and the solder joint can be determined by butt joining two pieces of ground wire together and then performing a simple tensile test. The important factor here isn't so much the numbers, but whether the sample fails at the solder joint or whether it fails in the wire. If it fails in the wire, the solder joint is at least as strong as the parent metal. If it fails in the solder joint, it doesn't necessarily mean the solder is not suitable for manufacturing, providing the breaking stress is high enough. Failure at the joint will either be because the parent metal solder bond is weak, or the solder itself is brittle and it has low elongation. So we took 1 mm diameter wire, we soldered them together using the torch method only for this test. It was a little bit difficult to do it in the furnace. And the results here show that only one sample failed at the solder joint, and it was again solder B. And looking at the marker section there on the left, we can see that the failure was through the solder and not at the interface, suggesting the mechanical properties of the solder were the problem here. The tensile strength that was recorded at 363 megapascals, or newtons per millimeter squared, is adequate for most jewellery applications, so there's not necessarily any need to worry about this. It's just not as good as the others in the test. And the results would suggest that mechanical properties of the solder have been compromised due to design considerations to achieve the desired melt range and the desired colour. So the third test we did was to simulate a ring sizing operation, and this is one of the most common jewellery repairs there is. So sizing is done by either removing a section of a ring shank and soldering the ends together, or inserting a piece of sizing wire into the shank and then soldering this. Either way, it's a typical example of a butt joint. So to do this, we took some test rings that we made from 3 by 1.5 millimeter round wire, and for each soldering test, we prepared 3 samples. The first sample we prepared with the joint faces butted close together and flush, and we used 1 piece of solder. The next, we actually used feeler gauges to gap it, and we gapped 1/4 millimeter, and then we used 2 pieces of solder. And the third test, we gapped it at 0.5 millimeter, and we used 4 pieces of solder. And for each solder to be tested using the hand torch, the jeweller was instructed to heat the sample until the pieces had melted, and then to remove the heat source straight away. For the furnace tests, the solder pieces were tack welded onto the rings to keep them in position. They were then placed on jigs and put through the furnace, and the furnace temperature was set to about 30 degrees C above the liquidus of the solder. And we evaluated the samples in the following way. We called the solder joint excellent if it was filled and we didn't need to do any repairs to the ring for it to be finished to an acceptable standard, and we scored it 4 points. We called it good if the solder joint had filled but it needed minor repair, and so we gave it 3 points. We called it average if the joint was filled but it needed major repair, and we scored it 2 points. And we called it poor if the joint had not filled enough and extensive work was needed, and we only scored it 1 point. And so here are some results for the torch soldered rings. So all rings with the flush joints were excellent, And we can see a little example on the left there. The solder joint was great. We did some microsections and they revealed some minor internal porosity, but it wasn't enough to be considered significant. And they still finished to an acceptable level. The good and the average results for the 1/4 and 1/2 millimeter gap tests were predominantly down to the joint just not filling fully, as we can see on those 2 right-hand pictures there. Some repair work is going to be needed to fill the joint in, but that could have been possible. For the torch soldered samples, the results were acceptable, except for when the gap became too large. All the test results here can be considered scoring relatively high points. And for the furnace tests, only 1 furnace was used, so it was the same belt speed, it was the same hot zone, we just varied the temperature of the furnace. And these are the results we got for the furnace soldered samples. So overall, they were inferior to the torch solder results, which is evident in the overall lower scores. Solder A performed very well, suggesting this solder is well suited to furnace applications, but the other solders did not, with solder B again having the lowest score. And if we can see some of the joints here. As with the wetting tests, like I said, solder B had evidence of the residual solder being present, and it had very poor wetting and very poor flow. All the other tests were acceptable, but needed repair to achieve an acceptable standard. So overall, hand soldering was far more forgiving than furnace soldering, giving consistent results. This doesn't mean that these solders are unsuitable for soldering in a furnace. It just means that significantly more effort needs to be made to set up the furnace. You need to set up temperatures and belt speed and dial it in for your particular application. The results also suggest that furnace soldering is going to be more susceptible to things like varying thermal loads on the furnace. So the 4th test we did was to solder a post on top of a cup setting to make earrings, and this is a textbook example of a T-joint. We used the same test criteria for torch and furnace soldering, and we tack welded the post on top of the earring before applying any solder. And so, unlike the ring sizing tests, all earring tests gave similar results for both torch and furnace soldering, and there was a negligible difference between any cadmium or cadmium-free solders. And again, all except solder B performed well, exhibiting good wetting and good filled joints. And these images can show you, up there on the top left, solder A, either with torch or furnace, sold very, very well. Solder C was the cadmium-free version of that solder. Again, solded very, very well. But solder B was awful in both applications. So why were these tests better overall than the ring sizing tests? There could be several reasons. First of all, the T-joint has a very close gap because the post is tack welded into position in the first place, encouraging a good solder joint. And also, the relatively low thermal mass of the pieces compared to the rings may contribute to this. And it's going to make the test less susceptible to furnace conditions. So the final test we did was to put a core and solder it into a tube. As we can see the pieces here, we designed it to be a loose fit. So we had a tube with an ID of 2.7 millimeters, and a wire diameter is a very loose fitting 2.5 millimeters. And these are the results. I'm not really going to go into these a lot here because the test was not very good. It was a badly designed test. All it really showed us was if the gap's too big, then soldering doesn't work very well. As you can see from the microsection on the right, there's lots of voids in there. And again, we see with the white solder in the middle and solder B, we have that residual piece of solder still evident in there. So that was the end of the testing, but what did the tests show us? What deductions can a jeweler make regarding the performance of the 6 solders chosen, and can we generalize some of our deductions? Well, first of all, it's very obvious that solder B was the worst performer by far. Soldering with the torch generally produced acceptable results, but the furnace tests did not. Had poor wetting, poor flow, and the pieces didn't fully melt. If they actually did, the results was lumpy and they were cratered. So do we consider the composition of this solder unsuitable for joining materials, or is it more to do with physical and mechanical properties? So let's have a quick look. Solder B had the worst tensile results, both for strength and for elongation. As we discussed, this doesn't preclude its use. It just may need to consider not putting it in a high-stress application. So it's probably not going to be great for ear post soldering. It's going to withstand fewer cycles before failure compared to the other solders. Other properties we can look at. Solder B has a very broad melt gap at 83 degrees centigrade. In a furnace environment, it's going to take a significant amount of time, relatively, to raise the temperature of this solder from melt to flow point. So both cadmium and zinc are included in this solder alloy to lower the melt temperature. In this case, the potential is there for either one or both to diffuse into the parent metal or just to volatilize off and change the composition of the solder that you've got left. Either mechanism will result in compositional change over a period of time in the furnace and will result in an increased melt and flow temperature for whatever solder is left. The new melt temperature or flow temperature of the solder might be raised sufficiently so it's above the set point of the furnace, so it's no longer going to melt or perform as intended. And that's probably why we see the residual piece on the furnace soldered test. So we gave this a quick test and we did some analysis on the residual piece of solder that was left in one of the solder B tests. And typically the solder's made up with 10% cadmium. But when we tested the residual piece, it only had 1.33% cadmium in there. So we believe this loss would raise the melting range of the solder above the furnace temperature. It's going to be less significant when using a solder with a narrower melt gap because you're going to achieve liquation very much quicker. And the problem is going to be less significant when the bench jeweler is using it for torch soldering, because in our case in particular, we instructed the jeweler to heat the workpiece until all the solder had melted. So all the solder's going to melt. So what else did it show us? Well, it indicates that if the liquidus of an alloy is lower than the solidus of the alloy to be joined, and the melt gap is sufficiently narrow, and provided the chemical requirements for wetting are fulfilled, any alloy should successfully join any other alloy. So to test this, we took combinations of standard jewelry alloys and put these through the ring sizing tests. So the tests were performed using the jeweler's torch only on this because the melting range of the standard alloys that we were using was actually too high for our solder furnaces. And we got some good results. So we used straight 14 karat yellow gold to join 18 karat yellow gold. So this is just normal 14 karat sheet, 14 karat wire, and we decided to use it as a solder, and it worked very, very successfully. You could arguably say that's one of the best results in the entire test, even better than the solders. So there's a 53-degree difference between the liquidus of 14 yellow and the solidus of the 18 yellow, and the 14 yellow has a 27-degree melt gap. And using flush joint faces, the results were excellent. So the same applied when we soldered the 22 karat yellow gold with 18 karat yellow gold. All the criteria for a solder were met and the results were achieved. A little bit not so good on the 18 palladium white doing the platinum, but those results were also acceptable. So this really showed us that you do not need special solder formulas for things to act as solders. All you need to do is fill the criteria and the operation should work. And the final observation involved joint geometry. So when the joint gap was a good fit, and with the flush ring test samples, we saw that, and the ear stud samples, the solders performed satisfactorily. What seems to be clear from these experiments is that the quality of the joint geometry, when it becomes less than ideal, then the solder performance decreases. And based on these tests, it's fair to say that furnace soldering will exacerbate some of these problems. Although torch soldering does not have the capability for volume production, the jeweler has complete control over the process and can turn up the heat to get the solder fully molten when they need to, and they have the ability to add more solder to the joint when necessary. Furnace soldering is a standardized process and well suited to volume production. And once the furnace parameters and the solder quantities have been determined and dialed in, this method does give consistent results time after time. And the main thing we take away from this is that probably the most important variable in any soldering operation is the joint quality. Even with the best solders, with poor joint geometry, the joint is going to be poor. So to conclude, we began by asking what makes a good solder and why do some jewelers love a solder and others hate it. So the two predominant jewelry soldering processes were used as baselines, and bearing in mind that any conclusions drawn were limited to the observations made using only the data available to the purchaser. So the colour, the solder grade and the melt range, etc. The following conclusions were decided upon. So cadmium-free solders perform as well as cadmium-containing solders in both torch and furnace soldered tests. Cadmium is known to help with wetting and flow, but the results showed there was no real difference. Furnace soldering appears to be more solder sensitive when you select your solder, and more so than torch soldering. When torch soldering, jewelers have total control of the heating and the soldering operation. The melt gap of the solder is an important property. A broad melt gap can decrease performance, and this is important because this is some of the information that's available to the purchaser. And the melt gap effect appears to be exacerbated when you furnace solder. Low melting point volatiles can be lost, and the change in melting temperature of the residual solder can potentially be raised above that you set on your furnace. And joint quality and geometry is very important. Tight-fitting joint faces give superior results. Large gaps between joint faces lead to inferior results, which require rework, repair, to get them to acceptable standards, and this is time-consuming and costly. So what we take away from this is solders are fillers and they are not joiners. Sorry, solders are not fillers, they are joiners. I got it wrong way around at the end. Yeah. So it's particularly relevant when we're looking at joint geometry or lack of, as the case may be, and provided the chemical and physical properties of a jewellery alloy meet the criteria for wetting, elemental compatibility, and melt gap is sufficiently narrow, it should be possible for any jewellery alloy to be used to join another one. And our final test demonstrated this. So, to define what makes a good solder, it's the ability to wet the parent metal, create a strong metallurgical bond without the formation of deleterious phases, and to have a narrow gap, melt gap, and that is all you really need. And why does one jeweller hate a solder and the other loves it? Quite possibly it's because a lot of soldering is done, and particularly at the bench, it's a very subjective way, and many decisions for or against how it performs are made based on non-technical observations. One possible reason could be that some jewellers don't pay enough attention to their joint quality. So the original problem we had at the company that I work for, Hoover & Strong, so we did a full investigation and we determined that the problem was not with the solder. All the criteria for the solders worked and they all fitted and they were all excellent. When furnace soldered, then something changed. And the problem was with the quality of the joints. So we analysed the production process and we found out that the assembly department had started to pre-finish all the components before they assembled them. It saved them time during their production process, but unfortunately, the effect was to round off all the sharp edges, making the overall fit of the components inferior, as you can see from this last picture here, large gaps. It resulted in the presence of these big voids, and so the solder was acting as a filler, not just a joiner. After soldering through the belt furnace, the components were joined, but not to a satisfactory standard that could be finished without repair work. And the porosity identified was, as you see, voids generated by a function of poor component fit. So we removed the pre-finishing step and the joint quality improved and we were back to normal. So thank you very much.
Grazie Stuart. Ricordiamo che la sessione di domande e risposte sarà alla fine, per cui comunque se avete qualsiasi domanda potete intanto segnarla sui fogli disponibili nelle vostre cartelline. E continuiamo il convegno con Chris Corti, che presentiamo, è un relatore.
So let's continue with Chris Corti, whom I'm going to introduce. Highly appreciated speaker at the Symposium of Santa Fe and TJF and JTF, with more than 40 years in the industry of precious metals with the World Council and Johnson Matthey, prior to setting up his own consultancy firm in 2009. He has perfected in metallurgy in Surrey, United Kingdom, and he's worked in the energy industry in the UK and Switzerland prior to moving to the precious metal sector. The title is Titanium, a Forgotten Alloying Metal for Jewelry Alloys. There is a consistent search for higher, tighter alloys for jewelry that can best meet the needs of modern lifestyles. In the last 30 years, there have been several attempts at developing improved resistance and strength alloys, for example, using titanium. So the benefit of titanium will be investigated for alloys with platinum, gold, and silver. Please, Chris Corti, you have the floor.
I don't know why you're clapping. You haven't heard me yet. Right. Good afternoon. The title of my talk is a question. Titanium, is it a forgotten alloying metal for jewellery alloys? In all precious metals for jewellery application, there is a desire for stronger, harder alloys, particularly at the high caratages and finenesses, that better meet the more demanding conditions of modern lifestyles. There have been various developments over the last 30 years or more to fulfill this need, but many have not found much commercial success to date. It was while researching my recent review of platinum jewellery alloys that I became aware of alloy systems that had showed much promise, but were never further developed to commercial application for jewellery. An example of this is described in a Johnson Matthey patent for the age-hardenable platinum gallium indium alloy, platinum 3 gallium 1.5 indium. In this patent, the inventors also refer to platinum gallium gold alloys as an option, with the use of yttrium additions of about 0.1% as a deoxidizer. The platinum 3 gallium 2 gold alloy is claimed to have a high hardness of 200 Vickers. Such gold alloys are said to cast well. In another example, Reixam, in his review of potentially promising ternary gold alloy systems for platinum jewellery, describes several alloy systems such as the platinum palladium ruthenium, platinum iridium rhodium, platinum rhodium ruthenium, and platinum gold rhodium that have potential in terms of good mechanical properties, corrosion resistance, and good colour. Another example is the use of aluminium additions to confer fire stain resistance to silver copper alloys, but such alloys have never found commercial interest. One alloying metal, hang on, did we not move? Oh. One alloying metal that has shown to be good at conferring high strength and hardness to the precious metals is titanium, and research to develop jewellery alloys for gold, silver and platinum is to be found in the literature, mainly for the pure metals. However, titanium-containing alloys have not found commercial interest despite very promising results. It begs the question, why? Has its beneficial use been forgotten, or are there other reasons for the lack of interest? However, recent work suggests that interest in titanium is being explored commercially now. I'm going to review the research work to date for gold, silver and platinum. We will start with the use of titanium in gold jewellery alloys. Jewellery in 24-carat gold, defined as 99.0% gold minimum, is the most dominant caratage in the Oriental countries of the Far East. But its poor strength and hardness leads to poor wear and tear in service. Recognising this issue, the International Gold Corporation, which is now the World Gold Council, funded a research programme in South Africa and Germany to develop a stronger, harder 24-carat gold in the late 1980s. This resulted in the development of 990 gold. It is a gold 1% titanium alloy. That is 990 fineness. So it is hallmarkable as 24 carat. It has mechanical properties considerably superior to 24 carat gold, approaching those of 18 carat golds, as we can see in the table. We can see that it has good hardness in the annealed, cold worked and age hardened conditions. The basis for selection of titanium for this alloy was the possibility of second phase precipitation, as an alloy containing 1% alloying addition in solution was cooled from 800 to 400 degrees Celsius, i.e. its age hardenability. From this, a table of probable hardening effectiveness was constructed, which we can see in the next table. The last column makes clear the reason for developing the 990 gold titanium alloy. The promise of the rare earths and zirconium are also noted. In the case of 990 gold, the precipitates are the gold 4 titanium intermetallic phase. The phase diagram, and I apologise for those of you that don't like phase diagrams, but it does show the limited solubility of titanium in gold at the low temperatures. The reason for limiting it to a 1% addition was to make the gold hallmarkable as 24 carat. Titanium acts as a grain refiner and makes the alloy age hardenable. While the alloy has attractive properties, it has not found much commercial interest, probably because it requires relatively sophisticated alloying and manufacturing techniques in a market where cost is a priority and manufacturing capability has been unsophisticated. It was possibly too advanced for its time. The beneficial use of titanium appears to have been forgotten for a decade or more, but more recently there have been a number of studies and patents where its use has been included. The use of titanium was explored in a study of 18-carat yellow golds with increased hardness by Soos and his colleagues at Mintech in South Africa. In particular, they were seeking alloys with a hardness in excess of 300 Vickers and targeted at applications for watch cases. They explored some 15 alloying metals, including titanium, and their effect on hardenability and colour. The table gives some results in terms of hardness for additions of titanium compared to standard 18-carat yellow. The target hardness of 300 Vickers was only reached with a 2% titanium plus a 0.5% cobalt addition. However, the alloys were a pale yellow colour and the formability of the alloys was compromised. So in their study, the use of titanium was not pursued further. They attributed the poor hardenability of the alloys to the increased solubility of titanium due to the copper and silver content of the 18-carat gold. And this reduces the amount of precipitate that forms and hence limits the potential increase in hardness and strength. There are some recent patents that involve the alloying of titanium into gold alloys. In the European patent in 2016, Montreuil Brejeux SA claim a lightweight precious 18-karat gold alloy containing at least 75% gold, containing titanium and other elements in certain proportions, some of which act as a grain refiner. The alloys of this invention have a moderate hardness of less than 300 Vickers, it is claimed. The main aim here is to produce lightweight alloys for watch and jewellery applications. With a density of only 4.54 grams per cubic centimetre, its use in alloying with gold can make a significant impact on alloy density and hence cost of jewellery. In another patent, a US patent in 2020, the inventors Pethe and Parab claim hard gold alloys of 18 to 24 carat containing titanium, zirconium and magnesium in combination for jewellery manufacture, again with a beneficial impact on alloy density. Hardness values of up to 260 Vickers are claimed. And lastly, in a European patent application in 2022, the inventors Guido and Colas claim gold and titanium alloys of 9 to 22 carat with improved properties, due in part to additions of a grain refiner for watch and jewellery applications. A major market for gold jewellery is 22 carat gold in the Indian subcontinent. With a fineness of 916, such 22 carat gold alloys are soft with hardnesses of about 52 to 70 Vickers in the annealed condition. Use of a much harder 22 carat gold alloy would allow lighter weight jewellery with economic benefit. The use of small cobalt additions and conventional alloying with cobalt plus antimony additions show some promise. But more recent work by Saradesh and his colleagues on additions of titanium to 22 carat gold have demonstrated that titanium additions act as a grain refiner and allow substantial age hardening. Some results are shown in this next table. And we can see, compared to normal 22 carat golds, additions of 0.5, 0.75 and 1% titanium. And we can see in the annealed, in the cold work and in the aged conditions, we get considerably higher hardnesses. And for hardness, you can read strength as well. The commercial use of a 22 carat gold alloy strengthened by titanium based on this work by the Titan company in India under their tarnished brand has allowed jewellery products to be marketed that show a 38% reduction compared to conventional 22 carat gold alloy, as we can see in the figure. The centre figure, I'll get it out in a minute. The centre picture shows a hollow bangle in their new alloy compared to a conventional 22 carat gold alloy bangle. And this is an example of where there's considerable weight saving. That's all I'm going to say on gold alloys. I'm going to now turn to the use of titanium in platinum jewellery alloys. Research by Biggs and her colleagues carried out at Mintec in 2005 has examined potential alloying systems for harder alloys aimed at 950 fineness platinum for jewellery application. Over 20 alloying metals were studied in preliminary trials at levels of 2% and 4% addition, and those showing promise were also studied at 3% addition. From this work, alloys with additions of titanium, zirconium, tin, gallium, germanium, magnesium, indium, and vanadium were studied in more depth. This work, along with consideration of other aspects, allowed the conclusion that the best alloy was a platinum 2% titanium alloy. This had cast and annealed hardnesses sufficiently low to be easily worked and formed, but with subsequent heat treatment, the hardness value could be increased by about 90 Vickers. Hardness values after aging at 800 degrees of 231 to 251 Vickers were measured, as we can see in the graph from their publication. The patent gives many possible compositions including a preferred one with a 2% titanium addition and one at 950 fineness with a 2% titanium plus 3% of precious metal. It is not clear whether this work has been developed into a commercial 950 fineness platinum alloy, but clearly shows a lot of promise. Lastly, I'm now going to look at the use of titanium in silver jewellery alloys. Some preliminary research on additions of titanium to silver has been reported by Wright at the 2013 Santa Fe Symposium. He compared the phase diagrams for gold titanium and silver titanium and concluded that silver titanium alloys should produce similar hardening results to gold titanium, such as the 990 alloy. A big difference is that the silver titanium system produces the intermetallic phase AgTi as the precipitate compared to Au4Ti for the gold system. This has implications for the volume of precious metal taken up as a precipitate. He also noted that the decrease in solubility of titanium on cooling to room temperature is much less in the silver system compared to the gold system. A further point was that the density difference between silver and titanium is about half that of gold and titanium. Thus, to get a similar volume of precipitate in silver would require about 4 to 6% titanium compared to the 1% we saw in the 990 gold alloy. Some initial tests on wire made in a silver 2% titanium alloy from a casting sprue indicated that solution treatment and age hardening were possible. The figure gives some results on samples solutionized for 2 hours at 800, quenched and aged. Wright cautioned that the apparent overaging effect is possibly due to local variations in composition in the samples. Further tests on samples made by 3D printing from alloy powder and solution treated at 900 shows a steady increase in hardness with titanium content in the range of 2 to 8%, with a hardness varying from 55 Vickers at 2% titanium to greater than 90 Vickers at 8% titanium in the solution-treated condition. A US patent by Vogel in 2012 describes tarnish-resistant sterling silver alloys that also demonstrate hardness. In particular, it describes a titanium-containing alloy with improved tarnish resistance and hardness. The composition is given as 92.5% silver, from 0.5 to 7% titanium, and optionally up to 6.5 palladium, and up to 7% niobium, as well as other elements. An example is given in the patent of a sterling silver alloy containing 5% titanium that can be work hardened and age hardened for 150 Vickers and with improved tarnish resistance. From these studies, it can be deduced that the principle of alloying silver with titanium can produce alloys that can be age hardened and would find interest in a jewellery application, especially as tarnish resistance is improved. Higher amounts of titanium than needed for gold and platinum appear to be needed for the reasons I've already discussed. The title of this paper begs the question of whether the use of titanium to produce harder, stronger alloys in precious metals has been forgotten since the development of 990 gold in the late 1980s. This alloy has not met with much commercial success in our industry, but it may be worth revisiting as our industry has become more technically advanced over the last 30 years. As detailed in this paper, the use of titanium as an alloying metal has been studied further over the last 15 years for gold, platinum and silver, and shows some promise, particularly at the higher caratages and finenesses. Its use confers good age hardening capability, and it has benefits in terms of lighter weight jewellery as it lowers alloy density significantly. As noted, one jewellery manufacturer in India has recently funded development of a titanium-containing 22-carat yellow gold alloy that is now in commercial production for jewellery application. Its use can lead to substantial weight saving with a concomitant lowering of cost. From the evidence presented in this paper, the use of titanium alone or in combination with other alloying metals facilitates good age hardenability for gold and platinum alloys particularly, but also in silver, albeit high levels of titanium additions are required for silver. There is evidence that it also confers improved tarnish and fire stain resistance to silver. So to answer the question posed by the title, the evidence is that titanium as an alloying metal had been forgotten, but it appears to be at the start of a new era in its use in precious metal jewellery alloys. So we can make the following conclusions, I think. The use of titanium in precious metal alloys confers good age hardenability to precious metal alloys, particularly at high caratages and finenesses. Titanium additions also act as a grain refiner in precious metal alloys. It also lowers alloy density, thus enabling lighter weight jewellery with economic benefit. And there is some evidence that titanium confers improved tarnish and fire stain resistance to silver alloys. So, final conclusion, titanium is no longer forgotten. Thank you very much.
Thank you very much, Chris Corti, for your very interesting presentation. Now let's change topic. The time has come to listen to Desiree Binternagel, CEO of Forever and member of the European Partnership for Responsible Minerals. She is an expert in precious metals with special focus on responsible supply chains. She has a Master in American Studies focusing on social injustice and gender injustice, inequality. She has worked in the high fashion sector and then in the gold sector. Dr. Binternagel with Forever matches a personal experience with protection for the environment and social justice, supporting the actors in the world of jewelry in the journey towards sustainability. The title of our presentation is The Advantages of Fair Trade and Fair Mind Certifications for Jewelers and Manufacturers. Sustainable ethical practices in jewelry are becoming more and more important, and it is therefore important to talk about non-profit certifications for trade and fair mind and all their advantages for all the actors in the supply chain. Desiree Binternagel will expand on these topics without neglecting challenges and interesting case studies to better understand the scenario. Mrs. Binternagel, please come to the floor. She is here at the JTF presenting for the first time.
Hello, everybody, and thank you for having the stamina to stay until now. I'm sure you're all craving for some coffee or an after-hour beer, but I promise to make it short. I learned a lot today, actually, and hopefully now that I know that most of you work with gold every day or you research about it, I can tell you a little more about the origin of this gold that you are working with every day. So I would like to start by giving you an overall overview about the global gold demand. I have some numbers here from 2022. In total, the world needed about 4,700 tons of gold, and most of it came from the mining industry, of course, so out of this earth. About 30% came from recycled sources, but of course this recycled gold has also been mined at some earlier point. Unfortunately, we don't know how this happened and when. In the best case, we are talking about post-consumer gold from old jewelry or electronical tools, but unfortunately, in the very worst case, it can happen that this gold was only mined a few weeks earlier than that. There is actually one study by the Swiss non-profit organization SwissAid that has found out that the United Arab Emirates buys gold from conflict areas such as the Congo or Russia, processes it and resells it as recycled gold. So this is also something we need to think about when we talk about recycled gold. Now, let's look at the gold that we know that has been mined. Most of that is coming from large-scale industrial mining organizations. So those are multinational companies that go into countries like Africa, have big organizations, lots of machines, getting the gold out of the ground. And about 20% of this gold is coming from the artisanal and small-scale mining sector. The astonishing part about that is actually that 90% of all miners do work in this very small sector, in the artisanal and small-scale mining. So 1 out of 10 people work in the large-scale industrial mining and are responsible for 80% of the global gold supply coming from mining. But a huge amount of people are dependent on small-scale mining, and the number will surprise you. It's more than 150 million people that are dependent on ASM mining. So this number is telling us basically one thing. When we look at the artisanal and small-scale mining sector, we can have a huge impact on countries of the global south, on the way that people are living in these mining regions. Unfortunately, though, the way that they live and work is more than precarious. So you can already tell by this picture here that it's not much fun to be dependent on gold mining. And also our environment is severely destructed by the gold mining industry. I'm sure most of you heard in the news about deforestation of the Amazon. And of course, we also have the toxic waste that is produced by gold mining. As most of you are from this sort of area, you are probably aware that we need cyanide or mercury in order to separate gold from the rock. And the gold mining industry is actually responsible for 180 million tons of toxic waste, and that is per year. So every year, this waste ends up in our environment. And then I'd like to show you a little video of how this toxic touch with mercury, for example, is looking like for the people that live there. So now we can start the video, please.
Before transforming the dust into gold nuggets, Marcel still has hours of work.
Ça se place comme ça. Vous voyez? Et on envoie l'autre comme ça. C'est dans cette farine qu'il y a l'or. Voilà.
Being heavier than the other residues, the gold stays in the hair of the carpet. When washed, the carpet releases the gold.
Voilà en fait le début du nouveau trou. Ce qui est en jaune. La poussière d'or. C'est l'or. Le métal le plus précieux auquel les gens en Afrique ici perdent leur vie pour ça. C'est ce métal-là. Voilà. Et c'est pas facile.
To mix the gold, Marcel uses mercury, a poison that he handles with his bare hands. The mercury then compresses the gold. To get rid of it, it needs to be burnt. The highly toxic smoke reaches Florent, the youngest member of the family. When inhaled, the mercury attacks the nervous system and all vital organs. This substance kills little by little, but no one is aware of the danger.
Ça y est, c'est fini. Il est devenu à la stable or. C'est ça maintenant l'or.
Marcel has never found more than this gold nugget of barely 1 gram.
So yes, this is a part that most of us don't think about when they buy their wedding rings, for example. But it's happening every day. And of course, I mean, if your biggest worry is how to support your family, you don't think about the mercury that you use. And they call it also a very a poison that slowly kills. Like, you don't notice it immediately when you smell, for example, the toxic fumes, but over the years, all these people suffer severe damages. And there's more problems. We have the problem of child labor. So children carry heavy loads out of the mines. Let's see if we can get the next slide. And actually, it's more than 1 million children that work in the artisanal and small-scale mining sector. So that's a huge problem that we have to think about. And we have human trafficking and slavery, something most of you probably thought doesn't exist anymore. But for example, in Peru, there's a very common system for the gold mining industry. It's called the cachorreo principle, where people are working for 30 days in a gold mine without getting any payment at all. And on the 31st day, they can keep whatever gold they find as their wage. Of course, the owners of the mine will make sure to send them somewhere where they don't find anything at all. So this is how people are exploited in the artisanal and small-scale mining sector. And I could go on and tell you more about that, but we also want to look at solutions today. Probably most of you have seen this logo before, maybe in the supermarket, on coffee or chocolate. So there is the fair trade certification, and it also exists for gold from artisanal and small-scale mining. Fair trade created a standard for responsible mining practices. And what you see here are the 4 pillars of the standard. So one part are the working conditions. This is about protective equipment for the workers, about health and safety trainings, first aid courses and health checks. Then we have the environmental protection, where it is about a safe and reduced use of toxic chemicals, the protection of water supplies, and renaturation measures. Of course, we have the social development of these communities, no abusive child labor, gender equality, and of course no link to conflict situations. And last but not least, it is about the organizational development, because we want to make those mines being able to work in a sustainable way and to improve their communities. So in order to create this standard, Fair Trade has connected with FairMind, which is an initiative that has formed out of the Alliance for Responsible Mining, deriving from one of the first responsible mining projects in Argentina. Another part of this standard for responsible gold mining is a minimum price for the gold that is being paid to the miners. 95% of the LBMA gold market price is the minimum that the mines get when I purchase gold from them. Of course, we also have the factor of demand and supply, so it can be a different price than that, but it has to be a minimum of 95%. And in addition to that, there is a social premium that the miners get, which has to be invested in order to improve the conditions under which the workers live and work. With fair trade, the social premium is $2,000 per kilogram gold. FairMind has a social premium of $4,000 per kilograms of gold. And there is even an ecological premium, which is used for mines that work strictly without the use of chemicals, and this is $6,000 per kilogram. So this comes on top of the price that they already get for the gold. And I would like to show you an example of how this responsible gold mining can look like. We are looking here at the landscape in Colombia, and I'm going to show you a short video of the mining cooperative Iquira, located in the Cauca region of Colombia. If we could play the video, please. Thank you.
La certificación FERMAI nos ha servido mucho. Primero que todo, se concientiza uno de que el impacto ambiental sea mucho menos.
De no destruir tanto la tierra porque tenemos las dos actividades, como mineros y como agricultores. Todos cultivamos el café, que el plátano, la yuca, el maíz, frijol, todo eso lo cultivamos en nuestra finca. Nos preocupamos por el medio ambiente.
Primero en el cubrimiento de salud, de la seguridad. Tenemos un trabajo estable, tenemos pues, beneficio para nuestras familias también, porque también recibimos un subsidio básicamente para nuestros hijos. En cuanto al estudio, básicamente lo desempeñamos en eso.
Aquí la comunidad también la hemos apoyado a lo que son algunas escuelas, a los ancianatos, a la parroquia de Pacarní, a la parroquia de Íquira.
La certificación FERMAI.
So with Fairmind and Fair Trade, it's all about the impact on the mining communities. And this is actually where it goes one step beyond the use of recycled gold, right? Let me show you some examples of how this impact can look like besides what you already seen in the video. So we have the building of roads, for example, where infrastructure is improved. Social facilities are built. What you can see on this picture here is a house that was built for the workers of a mine in Peru so they can have their meals in a warm setting. Things that seem very normal for us here in Europe, but they aren't over there, you know. We start with the very basic things. And then, of course, we have medical aid, so they get free health checks, for example, which is really important because those mines are often located in very remote areas. Another example I just saw last year when I visited a mine in Colombia, where the premium was actually used in order to pay a therapist to visit the mine once a week and give the miners the opportunity to talk to a therapist. And I mean, I thought that's really an amazing thing that they do, because this really changes the face of a community. You have a lot of problems in these areas. For example, in Colombia, you have hardly any possibilities to earn an income. And it's a very violent landscape that people live in, where guerrilla wars are still going on. So something as simple as that can really change the people's lives. And of course, we have the environmental aspect again. The protection of water supplies is really important. Most of you probably know that you need a lot of water in order to separate gold from rock. And we also all know that we don't have much water necessarily in all areas of the world. And renaturation measures. In the middle, you see a picture of a renaturation measure in the Andean regions of Peru. So after the gold has been mined in alluvial mining, this is an example here, the holes are being filled again, and the Mother Earth is put back on the top of the soil in order to grow plants again, because those people are also dependent on, for example, alpaca farming, and alpacas do need plants to eat. And we have the responsible use of chemicals, so it is promoted that they use alternative methods in order to separate gold from rock. On this picture here, you see actually a very natural method to gain gold. You just use a shaking pan. Of course, this doesn't always work. There's actually machines as well, like, for example, gravitation tables that are used in order to mechanically separate gold from other materials. So let's talk quickly about the advantages for the people over here. So we already seen how big of an impact it has on the people in the mining regions, but of course it also has advantages for people, companies working with those certifications over here in Europe or in the US. Everybody has to think about ethical sourcing nowadays, and of course you want to make sure that there were fair working conditions on every step along your supply chain, we have a social responsibility, and actually all these examples that I gave you as for the impact that fair trade or fair mine gold has, you can compare them to the European sustainability goals, and you will find most of them there. So if you want to work towards these goals, using fair mine or fair trade gold is an ideal way to do that. And then we have the consumer who's getting more and more interested in sustainable sourcing, and they want to consume in a responsible way. And of course, this also gives you the option to differentiate yourself from the competition. And needless to say that this also improves your brand image in the end if you have a very transparent supply chain. Of course, there are also challenges and considerations, otherwise we would not be here today because all of you would already use fair mine or fair trade gold. It comes with a higher cost, obviously. We saw that there's a social premium that is paid to the mines. There is a certification process in order to make sure that we do have these transparent and traceable supply chains. And one has to be willing to educate the consumer, because it is a very complex topic to understand that mining takes place no matter what we do. Even if we use recycled gold, the demand is still much higher than that. So there will be more gold mining. And gold has such a big value that people will not leave it in the ground. So one has to be willing to take that effort and inform people about why we are doing this. And then, of course, there are auditing and reporting processes that take a little bit of an extra effort for a company. But we do have some great case studies already that are working with fair mined gold or fair trade gold and are doing it quite well. A German jewelry company called Jan Spille has made fair mined ecological gold their unique selling point. They also use fair trade gold, and actually people are traveling from all over Germany in order to get wedding rings made from fair mined gold from this company, or fair trade gold. He actually offers both, so even better. So you can see it's something where you can really stand out and make it your unique selling point. And other examples, you probably know the jewelry brand Chopard. They have integrated fair mined gold into their supply chain and received much more media attention since then. High-class celebrities use Chopard jewelry and are really proud to be wearing an ethical jewelry brand. The requirements for certification are actually not as hard. I guess all of us have to do our bookkeeping. So if you can do your bookkeeping, you can also report your purchases and sales. Easy as that. Of course, you have to be willing to undergo an assessment and an audit, and be willing to undergo regular audits and reporting besides the documentation of your sales. In conclusion, I would just like to say that we all have to take on the responsibility to look at every step along our supply chain, and it is not enough to accept the status quo as it is, because we have seen under which precarious conditions the gold is mined, and we all have the chance to change something and improve people's lives by just looking at the origin of the material that we are using. So it's an easy thing because the gold still has the same composition, right? It doesn't change anything about the way that we work with it, but we have to be willing, of course, to pay this extra price, which I would say is the fair price for the work that's being done at the beginning of the supply chain. But especially with a product such as gold, which has such a high value, I find it would be the perfect opportunity to have an impact on improving the living conditions of people in the global south and create a social justice, which we all crave for, right? So thank you for listening. And if you have any questions, please come up to me. We can also talk afterwards, or you can tell me now. And I hope you all have a successful fair and learned something, and will continue to do so. And I'm happy to be here. Thank you.
Ringraziamo la dottoressa Binternagel.
Many thanks, Professor Binternagel. There is a slight change. We would like to conclude now with the last presentation, and then we will have a coffee break. So the last presentation is by CISG. We will have Emanuela Castaman and Antonello Donini. Emanuela Castaman is in charge of analytical and training sector of the Italian Gemological Institute. She graduated at Milano Bicocca and since 2006 has been working at CISG as an analyst. And she's also a teacher in training courses for the jewelry sector. Over the years, she acquired experience and knowledge in the interpretation of specific analytical issues, EX, EDR, for example, and UV. The topic of her presentation is certainties and uncertainties in gemological material analysis. The lack of uniformity in the wording of in the definition of the materials requires further investigation, and we need to update our knowledge. And I invite Emanuela Castaman to come over to the podium.
Allora, buon pomeriggio a tutti. Difficile.
Good afternoon, everybody. It is difficult to talk after listening to this last presentation. That for sure gave us all a lot of food for thought. However, the world of gems has some problems to come to terms with. We have understood that all over the world there are much more significant problems than knowing the geographical origin or a possible treatment of the gemstone. So let's quickly go through history. Since ancient times, men have always tried to modify the matter with treatments and methods to transform the gemstones found in nature into something even more precious, believing that a mine could produce more beautiful gemstones than the other mines, more transparent, more colorful. So this afternoon we will talk about origins and treatments. The geographical origin is today one of the most difficult topics for our industry. Most people, unfortunately, do not understand the complexity of the determination process. Some take advantage of this lack of understanding and trade gemstones, cheating about their provenance. The trade of colored gemstones requires laboratories to be able to tell them with a 100% precision the origin of the gemstones, and they want consistency amongst all the different gemological labs. But unfortunately, the science is not able to do this. We're confronted with a gemstone, and we have to try and go back into its history. Science alone cannot even get close to this for some gemstones, specifically for sapphires, i.e. blue corundums. So labs have to trust the experience of their gemologists and their familiarity with the gem material coming from the numerous deposits all over the world. This requires dozens of years of work. This is the reason why all gem labs stress that the determination of the geographical origin is an opinion. Every lab will give its own opinion based on a database. We're not talking about unquestionable facts. There are opinions, and there will be differences in the different certificates and in the different reports coming from different laboratories. Precious gemstones often come from remote areas, and some of these mines have a long history or may not even exist anymore. All this increases the interest and the palatability of a certain gemstone. That will therefore increase in value. The geographical origin can be an indicator, therefore also the rarity and beauty of a given gemstone. Some deposits have lasted only for a short period of time, therefore their supply is limited. An example of this is the Kashmir sapphire. Historically, it is believed that some deposits have a better quality of certain gemstones, for instance, Myanmar rubies. This can be true, but perception is everything. A Burma origin is more desirable and more precious. The first prerequisite for a lab to be able to issue a certificate on the geographical origin of a gemstone is adequate scientific equipment. This is very expensive, therefore small labs cannot afford this. But nevertheless, if a lab wants to certify the origin, it is necessary to have the competencies of gemologists as well as adequate equipment. The second prerequisite is expert gemologists, with a wide knowledge of the material coming from the different mines all over the world. And this is the most difficult part of the equation. Because, of course, you can buy the equipment. You just need money. But gemologists are not always experienced, and it is difficult to recruit experienced ones because some of them start working for a gemological lab, and that's where they spend the rest of their life. Then it is necessary to have a complete collection of known samples coming from specific mines, and you have to go to those mines and collect your samples as close as possible to the source. Gem deposits refer to geology, not geography, so borders between countries have nothing to do in relation to the place where the gemstone was born. The geological conditions can occur in different countries, and very often they do not follow geographical borders. Some deposits may have unique features, and they can be identified from others. In other cases, this is not the case. Labs, however, have the task and the duty to discriminate, because the trade requires a 100% precision. And sometimes they come to the lab saying, I already know that this gemstone comes from a certain area. The determination of the geographical origin is based on the idea that the precious gemstones coming from different deposits have different features, which is not always the case. Deposits in different countries may produce gems with similar characteristics. Some blue sapphires from Myanmar may have inclusions that are identical to those of sapphires from Sri Lanka. Conversely, in one single country, there can be different deposits of different geology producing different gemstones. For example, most blue sapphires from Madagascar come from metamorphic deposits. Others from basalt deposits, both to be found in Madagascar. So Madagascar's got this issue with two different deposits and different problems. When the determination of the geographical origin started, there were very few deposits, and usually they could be discriminated without a lot of difficulty. But since then, many other deposits have been found. Each one of these deposits started producing commercial precious gemstones, and the issue of the geographical origin became more complicated. Historical deposits have aged or may have become deeper or wider, so their characteristics may also change. What could be obtained in the past with standard gemological tests and a microphone is no longer possible today. It is necessary to collect chemical spectroscopic data. As the instruments become more complex, it is necessary to know them better and to interpret their data. Instruments have become much more expensive. Very often, it is necessary to have gemologists with high-level degrees in chemistry, physics, geology, mineralogy. This is particularly true with laser ICP-MS, where continuous calibration is fundamental to analyze different trace elements at lower and lower concentrations. So we need to be more and more precise. Another big issue is the acquisition of reliable samples that have to be tested when putting together a database. But it is possible that these samples are not accurate, and the only way to have reliable samples is to go directly to the mines and collecting them personally. A documentation of how, when, and where the samples have been bought is fundamental to set up a reliable database. A database of this type and the collection of information on samples obliges us sometimes to change what has been generally taken for granted. For instance, the orange fluorescence of the blue sapphire. For a long time, we used to think that this characteristic indicated the origin from Sri Lanka. However, as new deposits were found and more research was carried out, it became clear that orange fluorescence can occur in the blue sapphires coming from different metamorphic deposits of marmor type with a low content of iron. So this characteristic is now known as a useless one to define the geographical origin. Sometimes we do not manage to understand where a gemstone comes from. This may happen because of the overlapping of many features, or maybe because the features do not correspond to what we have in our database. In these cases, we have to say that the origin cannot be determined. And this is the truth. For all these reasons, reports on the geographical origin are an opinion. Some areas can be more easily discriminated, but the determination still is an opinion, based on the rigor of the analysis of all the above-mentioned points. Being an opinion, there are differences between the different labs, specifically when the determination is most difficult, like for sapphires. However, many in this industry believe that these reports are real, and they may be surprised and frustrated by the fact that different labs give different reports about the very same gemstones. Auction houses have understood that when they sell a gemstone with contrasting provenance, they often list all the certificates that have been written down in their catalogue, and the buyer will then decide what to think of the different reports. Some Sri Lanka blue sapphires are almost identical to the Burma sapphires, and for this reason they're called Burman sapphires. Some trading these gemstones call them the lucky Burma and sell them as gemstones from Burma, even though they know that this is not the case. Treatments. Consumers find on the market gemstones that have been treated. A particular gemstone may have been treated or not. Human beings change all crystals because they change their rough shape in faceted shapes that are also polished. These are the routine procedures for the production of precious gemstones. Next to cutting and traditional polishing, however, gemstones can also be treated to change and improve their color or their clarity. On top of this, the process can also change the durability of the gemstones, because these treatments cannot always be seen with the naked eye, and sometimes they're difficult to recognize also by experts. So if you sell gemstones, you have to describe the treatment procedure the gemstone might have been submitted to. If the treatment is not communicated, a person could think that a certain gemstone is of higher quality and more precious than what it really is. A further challenge resides in the fact that the treatment can be permanent, of long duration or short duration. Gemstones, when treated, can require special care. And we have a glossary that includes the terms that are often used in the nomenclature of the treatment of gemstones, and that you could find when buying precious gemstones. Finally, the treatments of precious gemstones are consistently modified and perfected, and the identification of the new treated gemstones is an important part of the ongoing gemological research. So some treatments are whitening for jade, pearls, and corals. It is obtained making use of a chemical substance to change the color of a gemstone and make it whiter. We often refer to this as the anti-age treatment for the gemstone. Surface coating to change the look of gemstones, applying a color on its posterior surface, or a substance which is used to coat all or part of a gemstone to change its color. Dyeing. Dyes are introduced in the pores of gems or in their fractures to change their color. Fractures are sometimes purposely carried out by heating the gemstone so that the material can absorb the dye. So fractures are caused so that the dye can penetrate in the fractures and give color to the gemstone. This is done in pearls, corals, turquoise, ruby, and emeralds. Filling of fractures or cavities. This can be done making use of glass, resin, wax, or oil to improve the clarity of the material, the aspect, and the stability of the gems, or in some cases also to add weight. This is done predominantly for rubies, emeralds, and diamonds. Heat treatment. A high temperature is applied to the gemstone to change its color and clarity. This is done for amber, corindons, berylliums, quartzes, tanzanite, topaz, tourmaline, and zirconium. HPHT treatment, well known for diamonds. Heating of a diamond at a high temperature under high pressure to remove or change the color. In the last few years, a similar treatment has also been used on corindons, specifically on sapphires. Impregnation. The surface of a porous gemstones is permeated by a polymer, wax, or plastic so that it is more durable and looks better. Turquoise, lapis lazuli, and jade. Irradiation. The gemstone is exposed to an artificial source of radiation to change its color. This is sometimes followed by heat treatment to further change the color. The second step is also known as combined treatment. This is done on diamonds, corindons, quartzes, topazes, and pearls. Laser drilling. This method is no longer very popular, but it used to be applied making use of a laser to produce, to try and remove dark inclusions in diamonds to make them of a better clarity grade. And then last but not least, diffusion. Permeation of some elements in the atomic reticle or lattice of a gemstone with the purpose of changing its color. This is done frequently in corindons. So you should always ask for a certificate that explains the provenance and the treatments. As you have seen, there are many, many different types of treatments, and very few gemstones are not treated. And it is only right to know about the origin of the gemstone you're buying. If you have the certificate of a gemological lab, you are more sure about it rather than just listening to what the trader is telling you. Thank you.
Ecco, adesso ho il piacere di invitare Antonello Donini, che è già stato relatore presso il JTF.
We can now leave the floor to Antonello Donini, who's already spoken at JTF. He's a technical director of CISGEM and has a lot of experience in gems, diamonds, and precious metals. Throughout the years, he has acquired experience with all gemological materials with an excellent interpretation of specialistic analytical techniques. He's the Italian delegate at IGC, the International Gemological Conference, the international conference gathering the best experts in gems all over the world, and coordinates the working group of the UNI Commission for Precious Metals and Gemology for the definition of the industry rules. His presentation will focus on diamonds, and the title is Diamonds, Natural, Synthetic, Some Tricks to reach some certainty or to express your doubts about what you see. So he's going to talk about the spreading of synthetic diamonds on the market. He's going to talk about the nature of the colorless gemstones that can be found in the trade. Many operators have not been informed or do not own the knowledge which is necessary to recognize these complex materials. For this reason, it is very important to provide useful indications to be able to identify natural diamonds, discriminate them from suspect ones, even though certainty can be obtained only if you bring the gemstones to a specialized lab. Thank you.
Bene, buonasera a tutti.
Good evening, everybody. Well, as you have heard, CISGEM produces analyses stating the nature and the quality of the precious material. We have heard about several issues and problems by Emanuela, and we have realized that our customers are really worried about these new synthetic diamonds. So we're talking about something which is very widespread. There are some correct actors who have launched lines of jewelry featuring this product, but unfortunately, some do not declare the real nature of their gemstones, and in some cases there is a lack of information. So, like Andrea told us, it is necessary to acquire certainty about the nature of this type of material. On the market, there are instruments and equipment that can be of help. You've probably seen such equipment stating that it is possible to recognize a synthetic diamond. As a matter of fact, the vast majority of these devices can recognize type 2A diamonds, which is the main topic of my presentation. Of course, there are also more sophisticated devices that will be much more expensive, that can help you much better but these devices considering the problems presented by people who come to us, I mean, in many cases it is necessary to know better what the synthetic diamond is, which are its features, to be able to interpret also what these devices tell you. So let's try to understand what a diamond type 2A is. Since the beginning of the previous century, diamonds have been submitted to scientific studies to understand their features, which have become more and more important also from an industrial viewpoint. In the last 50 or 80 years, we have acquired much more information about diamonds, which used to be quite obscure in the past. So in the 30s and 50s of the previous century, the diamond was classified in several ways. At the beginning, we had the two main categories, type 1 and type 2 diamonds. Type 1 diamonds contain nitrogen. Type 2 diamonds do not contain nitrogen. These studies are based on infrared spectrophotometry. You can see the two tracings at the bottom, and as you can see, there is a difference. In type 1 there is nitrogen, in type 2 there is no nitrogen, and the type 2 diamond therefore does not contain any nitrogen traces. And nitrogen is a trace element which is most frequently found in diamonds. Further studies have been carried out to better understand diamonds and to understand how nitrogen can be found in the structure together with other trace elements, and all these types have been defined. Type 1 with nitrogen, and type 2, where 2A technically is made up of pure carbon without any other trace elements. And then we have type 2B, which is a diamond that can contain boron. And lately, type 2C has also been added, containing hydrogen. We shall focus on diamonds of type 2A and 2B. What happens in nature? Of all diamonds that are mined in nature, only 2% is of type 2A. 98% is type 1, that is, containing nitrogen. In other words, type 2A are very rare, but even more rare are diamonds type 2B, almost 0%. So we're talking about two varieties, 2A and 2B, which are extremely rare in nature. Talking about synthetic diamonds now, we know that there are two methods today that are used to produce diamonds. HPHT, high pressure, high temperature. These artificial diamonds repeat what we believe happened in nature. Diamonds in nature were created through high pressure and high temperature. And then we have the CVD, chemical vapor deposition method, implying the conversion of a gas, methane or propane, hydrogen and carbon, in a solid on a substrate where carbon atoms are deposited, producing monocrystals. Both methods are used today to produce synthetic diamonds. And talking about colorless diamonds, or diamonds of grade J or K, well, all these diamonds are of type 2A. So if we can perform an infrared analysis, we realize that all these diamonds are of this specific type. So we're comparing something which is extremely rare in nature, but which is flooding the market today. Let's have a look at the different features. Let's see if we can find something that can be of help. So, on top of those devices that are present on the market and that can recognize type 2A. So, when we observe the diamonds, What can we see? And this is what I tell all those who come to our courses or those who come to us with a synthetic diamond thinking it is natural diamond. So it is always useful to carefully observe the gemstone because it can raise a doubt, a justified doubt. I mean, first of all, the dimension. Synthetic diamonds can be produced of any size. And there's a competition as to who produces the biggest artificial diamond. The biggest artificial diamond CVD production is 34.59 carats. I'm talking about the faceted, the cut gemstone. So you can find absolutely everything. Of course, you can then cut it in every way you like. But one peculiarity that we have seen resides in the fact that these gemstones, since the product is standardized, all have top quality cuts with excellent finish. This could also be a sign of alarm, the perfection of the cut. I have spent 43 years in the lab, and as you've heard before, if you end up in a gem lab, that's it forever, and I've spent 43 years in my lab. And I haven't seen many perfectly cut natural diamonds, but the artificial ones are all perfectly cut, with all the facets, perfect proportions. And in the press, in the international press, some time ago, there were articles about diamonds with a certificate provided by the best-known gemological institute. The certificates apparently were original. The gemstone had a laser incision, perfect sizes as reported in the certificate, and the certificate was also in the database of the lab. In other words, they took artificial gemstones, they cut them, and they made the laser incision identical to the one of the original ones. But let's move on. Which tools can we use to reach certainty or to raise doubts? If you have already attended a gemological course, you probably know about these devices. We recommend a UV light. It can be useful not only for diamonds, but for many other things. And you have to be able to cut the wavelength between long and short, 254 short, 365 nanometers long. Photoluminescence tools can also be useful, or just a laser pointer, the ones that you can find everywhere, provided that they emit a blue light or a UV light. Then you need a magnifying glass. And if you can, it is also useful to have a polariscope or a macroscope with polarizing filters. Well, we have seen that in 98% of cases, natural diamonds are of type 1. When nitrogen is present in the diamond, we have UV fluorescence, so if you expose a diamond to ultraviolet light, in the vast majority of cases, the diamond will produce a luminescence or fluorescence, which is blue purple in color. So if you have diamonds, you put them under the light and you see a blue color like the one that you see in the top center slide, or a purple color, then you can be sure that the diamonds you have in front of you are natural. They cannot be synthetic. But if you see strange colors, then you should start worrying. Yellow, green, orange. I mean, this does not mean that it is a synthetic gemstone. It could be natural, but usually synthetic diamonds produce these colors. And they can be totally neutral with regard to the long wave. Things change when we submit them to short waves, 254 nanometers. You have to be in a dark room, and when you observe the gemstone, you will see a difference if you look at the diamond with the long or with the short waves. Synthetic diamonds with a short wave produce a more visible, more evident effect compared to the long wave. In the vast majority of cases, natural diamonds behave in the opposite way. Stronger effect at the long wave and milder effect at the short wave.
CVD synthetic diamonds can have this greenish or blue color, which is different from the blue that you see above, with some fibrils inside, which reflect the deposition of carbon atoms which have occurred during this process. Now, if you look at them with short wave or long wave, you can also see some figures, butterflies or crosses, and this could be a bad sign. So you should have some doubts about these stones. So if you have this situation, you should bring these stones to a well-equipped and well-trained laboratory, and our company can be of use, of course. Then, speaking about ultraviolet rays, this is another important characteristic. Now, the diamonds produced by high pressure and high temperature, well, most of the stones that we have seen have this characteristic. They remain lightened. Well, it can happen also for natural stones, but this effect will expire in just a few seconds, just 1 or 2 seconds. Well, after 5 seconds, we have this effect, and after 2 minutes, it is still visible. So photoluminescence in diamonds is a very, very bad sign. Now, watching stones at the surface can be very useful. CVDs do not have natural surfaces because the natural surfaces are the remainders of what has been done by the cutters. And if we have these triangular figures called trigons, well, you can be sure that that stone is natural. It cannot be synthetic. Here, again, you need some experience. So the examination of inclusions can be a good sign. Well, people always look for a pure stone without any inclusion. But when I see inclusions, I know that inside those stones there is sort of the history of the world. I like them. Anyway, these are crystals which can have a round shape. Sometimes there are some clouds, black clouds which are distributed in a non-uniform way, and in other cases they can form shapes. Well, if it is a cross shape, it can be a bad sign. If we look at high pressure, high temperature synthetic diamonds, well, the tendency is to have highly pure diamonds, but sometimes there can be remnants of metals, because with this method we use a metal alloy in order to synthesize the crystal diamond. So you can observe such a situation with a given orientation, and if you observe them, they actually look like metal pieces. And CVD diamonds can be more difficult to identify. There are very few small inclusions with this shape, because in fact they are carbon residues, a carbon which has not crystallized. We are halfway between diamond and graphite, something amorphous, with some holes around. It's pretty difficult to see them, also for us. So it's not so easy to distinguish them from natural inclusions. Well, this can be very useful. But you have to have a specific instruments. Well, diamonds, natural diamonds can, well, if you cross the two filters, they can show these figures, which are called abnormal bifrangens, and they can have different shapes, different forms, which represent internal stresses of the diamond. And this is due to the geological history of diamonds while coming up to the surface. So synthetic CVD diamonds, and also sometimes natural diamonds, but please consider that these natural diamonds are very rare. Well, they can have these characteristics, which, however, are very stiff. Americans call them tatami, which recall the Japanese fabric. So they are either cross or linear. Again, you have to have a bit of experience, but when you see these figures, well, it's a bad sign, so to say, because you need further controls. Also because 2A diamonds can be synthetic diamonds, but they can also have been treated with a high pressure, high temperature treatment in order to eliminate the color which is present in the stone. 2A diamonds, synthetic diamonds, produced by PHTH, do not show these figures, so it means that they are empty. If you have the light coming from below, they do not show these colors. Well, consider that today there are some producers who guarantee the optical quality of synthetic diamonds, so without any lines, without any figures. So the quality of the diamond is certainly very, very high in this case. Naturally, as I said, there are instruments which, however, are pretty expensive. Instruments which can help you assess the diamond. They can tell you, okay, this is a good diamond, or there are some doubts about this diamond. And here you can also observe the spectrum. Well, in this case, you need some information because you need to be able to interpret the spectrum. color centers can be representative of the nature of the diamond, can be observed, but producers themselves will explain to you how to use this information. And you can detect whether it is a lab-grown diamond or a natural diamond. And as I said at the beginning, for further information, please call us at our association, because we are ready to help you. Thank you.
Thank you very much, Dr. Donini. We have come to the end of our series of presentations. Are there any questions for our speakers? 1, 2, wonderful. So please go ahead and ask your questions.
Okay, can you hear me?
We can.
Okay, Jorg strikes again. So he said, what's the possible importance of the solidus temperature? What's the possible importance of the solidus temperature of the parent material and or the difference in temperature between the liquidus temperature of the solder alloy and the solidus temperature of the parent metal alloy? Well, there is an importance, obviously. If the two are too close together, you will start to melt your parent metal before or during melting your solder metal. So there needs to be a decent gap between them. My guess is probably a minimum of 40 degrees centigrade, something like that. But it also springs to mind while looking at this, it's important for things like tarnish-resistant silvers, where you use either silicon or germanium as an aid in the alloy to make it tarnish-resistant, and it tends to sit out at the grain boundaries of your material. And it's going to be a lower melting point than the actual bulk alloy, so you might start getting grain boundary liquation if the temperatures are too close. That may also happen in extreme cases with some alloys when you investment cast them. When you do what we call wrought materials, so wire and sheet, you go through thermal and mechanical cycles, and it sort of normalizes and homogenizes the material. But a cast material is still got some form of solidification cycle. So the lower melting point phases are always going to be at the grain boundary. So that's what springs to mind. Any corresponding relevance of the liquidus temperature of the base metal material, in other words, the parent metal? I have absolutely no idea. I've not even thought about that. So I don't know. And the third question is similar. Any corresponding relevance of the heat of solidification of the solder alloy? So heat of solidification is the heat generated when the solder alloy freezes. There may be some relevance. Unfortunately, I don't have sophisticated equipment to look at that. Ulrich could probably help me out here. You do that by DTA or DSC, something like that? Yeah, so you could get that information. As to whether there's any relevance, you'd have to see the information first before I could say if there was or not. Thank you.
Good evening, Gardan Marchino. I am a chemist focusing in Liger Group of galvanic treatments. So I do not know much about gems, but I really found your presentation very interesting. And so I have a question for both for Dr. Donini and for Emanuela Custerman. Mr. Donini, you told us that synthetic diamonds can be made in every size, from point-something carats to more than 30 carats. In a few words, how do you determine the size of a diamond? Is it just a matter of time? Or are there any other parameters that need to be kept under close monitoring? Are you talking about production or the finished product? Production. Well, we're not expert in this respect. However, manufacturers of artificial diamonds say that the CVD process takes a much longer time than the other process, the HPHT process. Techniques are changing, they're improving, they're trying to change the chamber for HPHT processes, the chamber where the pressure and the temperature are induced. Anyhow, it takes weeks to produce crystals of a few carats. But some Chinese producers have enormous facilities with trains of these machines producing day and night synthetic diamonds. Most of these diamonds are used for industrial purposes, but some manufacturers also produce synthetic diamonds of gem quality. And you can find them in the internet. Well, talking about cut, I would like to tell you about the following case. Recently, we found a gemstone of 5.61 carats produced with the CVD process. And at first sight, it looked very similar to an old mine carat with the old irregular cut. But then we looked more carefully and we saw that it had been cut on purpose to simulate a gemstone that was traded 50 or 60 years ago in terms of cut protection. So on purpose, the cut had been made so that the diamond would look old cut. So I've told you that there is a standardization, but sometimes you also have this kind of cases. With the CVD process, it takes a few days. Slabs are produced 1 centimeter thick, 3 by 3 centimeters, and you can imagine what you can obtain from these tablets. But if I want to produce 1 carat or a 10 carat, I mean, does it mean I need longer time? Of course, because it is a deposition. The longer the time, the bigger the deposition of carbon atoms. I have a question for your colleague now. I believe I understood that gemology labs, to issue a certificate of origin, express their opinion. It is a matter of opinions. So my question is, are there groups of labs that are more reliable than others, the opinion of which can be viewed as more reliable? And if yes, how did this lab acquire this kind of reputation? Well, we are part of a working group called LMHC. It is a group that aims at harmonizing the situation. That is, we are trying to define standards which have been distributed to the 7 most famous labs in the world to be more consistent and more uniform. But the problem is, number one, these 7 labs do not have the same type of instruments. Some labs have more advanced equipment, so they can look for the percentage of trace elements that maybe other machines are not able to identify. So some labs certainly have a much higher level of precision. And therefore, they can confirm the provenance with a higher degree of reliability. However, as I told you before, the experience of the gemologist is the most important aspect. So the analytical and instrumental data are useful, but we have to evaluate a mix of aspects: observation under the microscope, the experience of the gemologist. So the gemstone is viewed not by one single person, but by 2 or 3 persons, including the head of the lab, in this case, my colleague, who confirms the origin But it is still an opinion, because unless all the features confirming one single origin are present, then it is an opinion. If most of the data indicate that it comes from Burma, but the inclusions are not always characteristic of the origin, then you have to try and express an origin, but in the awareness that this cannot be 100% precise, unless you do like an auction house that try to have different certificates, and it might well be that a gemstone results as of a certain origin in all 3 different labs. Or maybe 2 labs give an origin and another lab gives another origin. So nobody will ever know which is the origin of that gemstone, for sure. We do not have an identity card of the gemstone. So it is just a matter of still there is a lot of uncertainty. And the smallest labs that do not have the equipment to evaluate all the characteristics, they just use the microscope, and this is quite limiting. So their opinion is not so well determined. I mean, we are not 100% precise, even though we have the best possible tools. Small labs are even less accurate, so if you want to have a certification, it is much better to go to a big lab that is generally recognized. Thank you. Well, I realize that we have passed over a pretty strange message, that is, labs give you a certificate of origin, but it is not reliable. Well, things are not exactly like that. The certificate of a lab is important, and it might well be that a person obtains different certificates, and very often we give the same origin. There is always a direct exchange amongst the different labs. For sure, with the advent of all the treatments Manuela told you about, carried out on rubies, emeralds, sapphires, it has become really very difficult, because treatments change the gemstone. We're almost at atom level. So sometimes, I mean, if the gemstones have been in the trade for many, many years, things are easier, because you already see the gemstone that comes from the beginning of the previous century with certain inclusions. Things are easier, but recent gemstones that have been heavily treated, in many cases, are modified, and it is much more difficult to evaluate them. We're like doctors. Doctors collect many data. When you go to the doctor, you say, I've got this. And the doctor says, OK, let's have a radiograph, a CT scan, a complete blood test, and so on. And then all these data are put together, and the doctor can make the diagnosis. This is what we do.
Bene, se non ci sono...
Very well. If there are no other questions, we can conclude the 19th edition of the Jewelry Technology Forum. I would like to thank you all for remaining so late. I'd like to thank all those who have been with us online. This event has been broadcast on social, and it will be put on social media, and in our website. In a while, you will find the proceedings of the meeting. So thank you, and all the best. Thank you.